Okay, let's take a look again at some vocabulary. I think you'll like these slides here. We want to make sure we leave this video knowing the difference between a sequence and a series. So we recall that a sequence is just an ordered list of numbers. And we're going to assume that this is an infinite list. And we can also think of it as a function. Oh, and I like that. It's down here. A sequence may also be defined as a function. Like every output a sub n is a function of n, where n is defined for the positive integers. So a sequence is a list. A sequence is a list of outputs, and we can think of each term as a function of its index. On the other hand, an infinite series is a sum. An infinite sum. A series is a sum. So yes, we're given a set of a list of numbers, but we're going to add those terms up. We're going to add those terms up. So one way to write that is just a sub 1 plus a sub 2 plus a sub 3 plus dot dot dot. Or in a more compact form, we have a new index we'll call the index k, and we say that k runs from 1 to infinity, and the terms of the sum are a sub k. Alright, and that, so back and forth. We've got a sequence, which is a list, and then from a sequence we can define a series, which is a sum. A sequence is a list, a series is a sum. Now there's something else, another mathematical object. We're going to define this new sequence, and it's the sequence of partial sums, where the first term of sequence S is just a sub 1. The second term of sequence S is a1 plus a2. The third term of sequence S is the sum of the first three terms of our original sequence. And the nth term of sequence S is the sum of the first n terms of our original sequence. So we can use summation notation. Looky here. I'm highlighting this here in the center of the slide. We have that dummy variable k because we're going to index from 1 to n. We want to add up the first n terms. So we've got this compact way of writing that where k runs from 1 to n, a sub k. We're summing them up. And we can talk about in a little bit the convergence or divergence of the infinite sequence. And that means we'll be taking a look at a limit as n goes to infinity of the partial sums. And a partial sums is this new sequence we just defined, this new sequence, sequence S of n. We want to see if it converges to L. That's going to be the flavor of the remainder of this chapter. Okay. Now I like this table. That's why I really made this little PowerPoint for everyone. Column 1 has mathematical objects that have to do with sequences and series, and column 2 kind of takes us back to the first half of our calculus book where we were using functions. And I've talked about how these are mathematical objects where the elements are discrete, whereas functions are defined on continuous intervals. Okay, so here, look at the notation. For sequences, our independent variable is n, the index. Our dependent variable is a sub n. So input n, output a sub n. Whereas for functions, we were using input x, output f of x. Okay, but those objects should correspond to one another. For sequences, the domain were just integers. Those are discrete. For functions, the domain was real numbers, which is a continuum. And here the examples. We would talk about the set of non-negative integers, 0, 1, 2, 3. Or we can talk about non-negative real numbers, x greater than or equal to 0. Well, we want to talk about adding things up. And when we accumulate a bunch of terms, we call that a sum. But if we want to describe accumulation under a function that would be called an integral. So we can talk about this partial sum, which would correspond to the definite integral. Here we have a finite interval from 0 to n. We have a finite number of terms for this sequence. And you know where we went later is we went to these improper integrals on an infinite interval. And we have these improper sums called infinite series. Okay. So this is something from your book you may want to look at. I think that's pretty neat. Let me check out my last slide. Oh, just because I know what's coming up in our in the next course material. So I had a video on geometric sequences, and this theorem is going to talk about that mathematical object called a series. So see, we have this series notation, k equals 0 to infinity, adding things up. And we're going to have that common ratio again, r to the kth power. We can have this coefficient a can be any real number. I guess if it were 0, this wouldn't be very interesting. But this theorem talks about a special type of series or accumulation. You have the common ratio r, a real number a, and if that common ratio's magnitude is less than 1, then this infinite geometric series is going to converge. And what will it converge to? This is going to be one of the few series that will actually know what the limit is of the series, and we will get the number a over 1 minus r. And it goes on to say if the magnitude of r is too large, one of two things can happen. If r is bigger than 1, there's a way it converges, and if r is less than or equal to 1, the series converges. So not to be confused with the geometric sequence from the previous video. Thank you for your attention.